does anybody have questions regarding the presentation?
Pero pareha pag gihion ang iyong foam sa sandigan ng gari. Sandigan ng librano.
It depends, no, kay we have different values for hardness and density. Usually, dapat depende sa car. Yes.
Pwede na siya gamitin sa strato din.
So, kita ninyo na the density.
Sa mostly sa common sa kanong gari. Pero siguro tao to pero
So, diha na
lagi pareha density sila.
yes, diha na makita sa comfort o sa material nga gi-design igamit. So, if mo ang buwan, ganahan kay humok mo ang foam or
Pero
whatever.
mag-create ka ng foam diya. Okay, unsay mga properties na mahimo siyang foam?
Sa plants, ang ilang buhaton kay they use the solution. So, most of the time it's polyurethane. Kanya spray na nila, spray na nila, build na ang foam.
Kaya ako plano magbuhat magkuha ba?
Pwede ra, kay nabuhat mo na mo diri. Nasa tay murag custom material nga spray.
Spray na ganyan.
Oh, manual para maka-form na tayong anak. But I would think it would entail cost.
Plano na ko pulling ang kwan bisa sa amin balay.
Oh, see, anything else? Namatay ang activities sa gawas. Let's go.
Any other questions?
Okay. Thank you very much for spending time with me. I need to go take a
Okay, so next up, let's please welcome our next presenter, Miss Maria Malu Suarez.
Good afternoon. I am Malu from FEA. I am with my colleague Richard and we will be talking about the FEA capabilities. So to start with, when you hear the word FEA, what usually comes to your mind? Usually it's simulation, right? Virtual simulation or any physical testing being converted virtually. So first, let's define FEA. What is FEA? So FEA stands for Finite Element Analysis. So why it's called finite? Because we are dealing with countable number of elements used to represent a structure. So what you can see here, the squares and the triangles here, used to represent the part, they are called elements. So they are the small section of the part being analyzed. So depending on the complexity of the part, let's say a stump part or a part with a uniform thickness, they are being represented by 2D elements, these triangles and quads. And for those geometries like foams, like plastic parts, they are being represented using 3D elements, the tetrahedron, the hexa, and the penta. So it's called analysis because we subject the part into a boundary condition, we put loading conditions, and then we analyze the part. So basically, FEA is representing a numerical or a mathematical model, understanding its effects during the product life cycle. So it's like predictive analysis, what happens to the part. So when and why do we do FEA? So we do FEA in the 3 stages of product life cycle. So first, before the product is designed or before we were able to come up with a CAD design. So in this stage, we are helping the engineers create the feasible design. So what you can see here, it's just what do we call design space or a boundary being bracket design. So we have already identified the fixation points, what will be its performance targets. So from there, we are trying to find out what will be its optimum design or what will be its optimum material distribution in order for this part to satisfy the customer's requirement. So the red that you are seeing there, so the red parts, those branches, those are what we call element densities. So those are the flow of forces or the flow of energies from the load application points up to the fixations.
So muna yung vertical area.
These are, let's say, if this is the part, dira ga flow ang forces. So which means that material is needed in designing a bracket. Yeah. So the designer needs to consider, this is how the energy flows. So which means that this area, we have to have material in this area because there might be some cases that we have a design but we don't have energy flow on it. What you can see, the blue parts are totally non-load bearing elements. So walay load nga naga-flow diha dapita. So this information, we give this to the designer and we let the designer understand or interpret this so that he will be able to create a bracket out from this design space. So, other analysis that we do prior to CAD design or prior to CAD creation, except I mentioned a while ago the topology optimization, wherein we are trying to find out the optimum shape or the optimum material distribution. We have also what we call topography optimization. So, unsa ning topography optimization? The topography enables us to identify the optimum bid and swage location for a part in order for this part to be reinforced or to have extra stiffness. So that's the time na nga makadetermine na ang designer, diri na ko ibutang akong swage, diri na ko ibutang akong bids with a specific bid height or swage height. So another type of optimization that we do is, we call this free size optimization. This is useful especially for composite materials because in this optimization, we are trying to find the optimum thickness distribution within a part. So imagine this is a carbon shell, this one. This is a carbon fiber shell or a glass fiber shell. So we are trying to find out what will be the optimum thickness distribution in the entire seat structure. So the other optimization that we do is, the other one is size optimization, wherein we are trying to optimize the thickness for these rib parts. Like for example, this one, it's a plastic back frame. So each rib here, we are trying to optimize what will be its optimum thickness that we can achieve this certain level of stiffness. Because as you can see, this red part, it's weaker. It appears to be weaker compared to this picture here. So, and the last one is the free shape optimization. So this optimization is used to identify the stress concentration areas. So as you can see, by just merely changing the radius of this clip, we can reduce the stress concentration in the clip. So these are the optimizations, or these are the FEA that we are doing prior to CAD design, so that we can help the designer create a more feasible CAD design. So next, so after the product is designed, so once we have already the CAD part, we validate the defined design. So in the previous slide a while ago, this was still a design space, right? So now it was converted into a bracket. So once we have the bracket design already, we need to validate if it satisfies the customer requirement or it passes through the certain regulation or load case that the customer or the OEM requires. So this is the time that we validate the part. This is just a part example, but we usually validate the complete seat structure. So last but not the least, so after the product is released, we investigate product failures, especially if in FEA we do series of validation. So after that, we do the physical test. So once there are failures in the physical test, it will always go back to FEA why this failure is not predicted. So that's the time we investigate. We try to investigate and then correlate our model, and then from there we create a model from that failing part and we do the improvements. So I will be showing to you the basic FEA steps that we are doing. These are the basic steps. First, we mesh, then we assemble, we do the load case setup, then we submit our file for calculation, then results analysis. So first, we have the geometry from the CAD, from the design team. We receive it from them. We do the mesh. We create the mesh representation for those parts.